So hello everybody. I'm here because at IBM we some months ago we started a work group where we meet let's say 1 or 2 hours every week, and we discuss concepts of first failure data capture for Linux. First of all, I work in the IBM lab in Böblingen, which is also here in Germany. It's about 400 kilometers south from here. And yeah, we are 4 people working on that topic. And 2 of us are here today. So Michael Müller is the second one. So we are 2 from IBM here, and we want to discuss with the community our insights and our results that we produced during the last month. So we were quite happy to hear that the Tracing Summit was in Düsseldorf, and we took the chance and we hope that we can discuss this with you. Besides this presentation, we have a BOF this evening at 5:30, and it would be great if some of you could also be there. Then we have more time to discuss details of FFDC. So this is my agenda for today. First, I want to tell you the principles of FFDC, the concepts. Then I will show you a short proposal, some things that we have discussed during the last months. We had some ideas that we want to share. And then the last point will be an action plan where we defined some actions that could be useful in order to increase the FFDC qualities of Linux. So short motivation. FFDC is, and that's why we are here, it's for problem determination. So we have detected a symptom of a problem. So we ask some questions. We have to ask some questions. So we detected that the system somehow did not do the job that it should do. Which problem led to the symptom? And often you ask yourself which component was responsible for, or which component, in which component the problem did occur. You need that in order to narrow. You have a complex system, and you want to narrow down the root cause of the problem as far as possible. So you don't want to read the source code of the whole system. You want to know the component. And of course, the problem does not mean that you have understood and found the root cause. The root cause can be even farther back in history than the problem. And of course, which sequence of operations then triggered the problem. And for this, normally you have trace records. Current approach under Linux, as far as we see it, is more targeted for live debugging. So you log onto the system, you switch on trace points, you work with the system in order to find out what is going on. And you often have to reproduce your problem. But what should you do if this is not possible? For example, we come from System C, mainframes, and customers do not let us log on to their systems. So we are not allowed to do that. So or embedded systems where you can't log on, you don't have remote access. So in this case, you should record automatically every information that is necessary to analyze the problem and to find the root cause of the problem. And FFDC is a concept how you can achieve that, or at least we hope that we can achieve that sometimes in the future. What is FFDC? That's a joke I wanted to put on the slide. So decimal FFDC is 65,500. Not so funny. Yeah, okay. FFDC means first failure data capture. I think it's a term that IBM has invented. Not sure about it, but I think we have invented it. So in case of a problem, the problem has to be detected automatically. The system has itself must have the feature to detect problems. Then you need to gather enough information to analyze the problem, and the data get to be collected. And in this case, the second point means during the system runs, you have to collect enough information, history information. And an important point is that the first occurrence of the problem has to be recorded. This is in contrast to tracing, for example, where you have wraparound buffers and you overwrite old records with newer ones. For FFDC, you want to save your first set of debugging data. And if you don't have enough quota for another one, you will throw away the second one in case. So working FFDC means there is no need to replay a problem situation, and also working FFDC means your system is configured. You don't have to do manual configuration, it's just set up for FFDC. And of course, if you have a product that fulfills a certain service, a certain requirement, all the relevant component of your product, for mostly kernel and the relevant user space processes, have to be enabled for that. Here are some examples of available FFDC under Linux. For example, Android, or not only under Linux. Okay, Android is almost Linux. I developed an Android app the last month in my spare time. And when you, Google provides a service, so when your application crashes on the Android device, you get, as user, the question, should I report the data? And if you enter yes, the developer, and that was me, you get a problem report, and the problem report, if you log on to the Google Developer Console, you get a problem report and you see the stack backtrace of your Java application. That's one kind of FFDC. So data is collected automatically, and it's even sent automatically to the developer who is hopefully then able to find the bug. There are some other examples. For example, last week when I prepared the presentation, I got that one, and then I made a screen capture in order to show it to you. The KDE has also something, some report mechanism, and also here you get the stack backtrace. There is some, for example, Red Hat SOS report, it collects data manually. So if an operator detects a problem, it calls SOS reports, data is collected, and it's manually sent to Red Hat service. And of course, System C firmware, that's where we come from. And that was the reason why I'm here now, or we are here now. Because we had a project together with our firmware colleagues, who makes the firmware for the mainframes for the System C, and they have, as I said before, they have no access to customer systems, so data has to be automatically collected. Enough data has to be automatically collected, and it's automatically sent to IBM. Can be automatically sent to IBM service in case of an error. So they have much experience collected over the last 40 years, and that was the starting point of our work group. Of course, we all know there are constraints for collecting debugging data for tracing. We don't want to spend resources only for the case that something went wrong, because we want our system to do the work that it was designed for, and not for collecting debugging data. So we have to take care that we don't consume too much of that. And time to recovery is also an important point. Therefore, you don't have to collect too much data for FFDC, because that takes time until you can restart your system. And many people also from our firmware team have told us that perhaps 2% overhead might be some value that might be acceptable. But of course, that is probably something that can be discussed. So what do we need for FFDC? In a perfect world, of course, you want to have everything. You record every state change on your system, and if your system detects an error, you save the complete state of your system. That would be perfect, because then with that data you can replay, you can go back in history, and you can reconstruct every situation of your system. And of course, you can then also reconstruct the problem situation when, for example, a pointer is set to 0. That would be great, but of course it's not doable. You would have to trace, or you would have to record every non-reversible operation. And if you have a memset of 1 GB in your code, you would have to collect 1 GB within a microsecond, and that's just not doable. So that would be nice, but it's. I always thought if you are religious, for example, the God probably must have such a system in order to see all your sins afterwards and prove that you did something wrong. So that must be the system of the yeah. So what's doable is you have to get the relevant data. So you have to trace. You have to get history. So we have to trace the relevant data, and we have when the problem is detected, we have to collect the relevant state, and the relevant state are mostly the component control structures. For example, if you want to analyze a scheduling problem in the Linux kernel, one control structure which might be interesting for you is a task struct. If you are interested in a memory management subsystem failure, then probably the struct is something you should save. What is also important is to partition your system. Your system consists out of many, many components, and you don't want to get the state of all components, but you want only get the state in order to reduce the data amount of the affected components. So if you have a networking problem, it probably makes sense to collect only networking subsystems and not blocker subsystems, for example. We have to detect the relevant errors, so we have to define error classes, and we have to define what should be done for an error class, what should be collected. For example, one error class could be your file system performance is bad, and in that case you collect data of the SCSI layer and the block layer, for example. Advantages of the doable approach is, of course, besides of reducing downtime and runtime overhead and disruptiveness, because you don't have so much data, is, of course, you have less data to analyze, which is often also a good thing. So you have, in advance, you have concentrated to the data that is relevant. Therefore, afterwards, you don't have to analyze so much data. Which types of debugging data we have? We are at the Tracing Summit, so this is probably nothing that is new to you. So we have logs, like syslog, for example, where each log entry contains information about a long-term relevance event. Then we have traces, where we remember important steps of the system. which is normally not persistent, and we most of the time use wraparound buffers. And we have dumps where we copy the current state. And so we have logs and traces which contain history information, and together with the current state we can reconstruct some parts of the history of a system, which is needed in order to analyze a problem. What might be missing, that is what we identified in our discussions, and that would be great if we could discuss this with you this evening. One thing where we think which might be missing is a component state safe, so that there is some mechanism so that you can extract the relevant state of a component. As I said before, if you want to have the relevant state of a scheduler, you might want to have the task tracks of the running processes, for example. So selected component internal state. We had several discussions how we should name that. Currently we say state safe or snapshot or component dump. So like trace points where we do that for traces and we define which points in the data flow is interesting, it might be good to have something for state. So to save, if you detected a problem, you save state. And then FFDC log. A problem that we saw in Linux kernel development is that sometimes you have some relevant data which you want to log, but normally you don't want to do a print k because relevant data for developers, for example, register contents or a hex dump of a buffer of control data or something like that. So something happened and you want to log that. And not sure, normally you don't want to have this in the print k in the syslog because syslog is most targeted for system administrators. So we think it might be useful to have some, we call that FFDC log, so a log for developers. And last point, FFDC statistics. It might be useful to have infrastructure for statistics. Statistics can be used to reduce the data that you have to record. For example, if you have recovery actions, so you could trace every recovery action and then count them and say, okay, if I have one recovery action within 1 hour, it's okay, but if I have 100, it's not okay. So one mechanism is you trace it, so you have to keep all the 100 events in, or you make a statistic which is data reduction, and you use a statistic for FFDC, for example. Then what we think what is missing in Linux is some standardized way to transport the debugging data if you detect an error. So for FFDC, as I told you before, we detect the error automatically, and then we have to transport the data somehow to a repository where we store that data. And from that repository, for example, you can do this reporting and send the data to the developer. So we think we need snapshots. We call that snapshot to collect the data into a package, maybe a tarball or a CPIO archive, for example, and a repository where a centralized place where you can put that data, where this is stored. And in order to use it, to create those snapshots, we probably need an API for that, and both for kernel and user space. So we have drawn a picture how this could look like. It's not so complicated. what we want to have is a repository to store those FFDC data. And for the kernel, each component can use the Snapshot API to create those snapshots. And with the Snapshot API, as I said before, you can collect the important data for the component. And you can, and one part of that is probably also to collect traces of that component. And then you push the snapshots to user space. Probably we need there some daemon that gets the data out of the kernel, and then it is stored in the repository. And the same thing, in our project, because we also do KVM on System C, the KVM team is interested to do that for QEMU, for example. That's a part where Michael Müller is working on. So the same thing in user space. And also in user space, sometimes if your component is not able to detect the error, there might be processes that have more knowledge about the whole system, monitor processes that monitor your system, for example, do some sample file I/O and measure the response time. And then, of course, also these monitor programs should be able to create snapshots that are then stored into the repository. And if we have that, we need some reporting housekeeping infrastructure so that you can look at it into this store, see which snapshots are there. Maybe you need this reporting mechanism so that it's automatically transmitted the data to the developers. So this is this API we thought that might be useful, that can be used to create the snapshots. We have a register function where each component can register at the FFDC subsystem. Then you have a snap begin where you start the snapshot. Then we could add some metadata that describes the contents of a snapshot. For example, you can say, okay, this is a task struct. Then you add binary data, and for example, you add the task struct data to your snapshot, and you can do that multiple times. So you get several blobs and metadata in your snapshot, and then you call end, and it's then transmitted to the daemon. And we have a snapshot callback where a component can register a callback, and the callback is triggered if, for example, a monitor program decides that I need a snapshot of the SCSI subsystem, for example, and the SCSI subsystem has registered at the FFDC framework. Then the callback of the SCSI subsystem is invoked, and in this callback, the SCSI subsystem collects the important information. That is the basic idea that we had in mind. As I said, we saved the relevant component state. It has the advantage if the component itself does it. The component can use its own locking in order to make the snapshot consistent. It locks the task structure, the task list, for example. The kernel can lock the task list, get the task struct data, unlocks it, so you get a consistent snapshot. Our idea was to put it somehow in debugfs. Now we are talking about kernel snapshots. Debugfs, for example, we can put in a snapshot stream attribute that is read by the daemon to get out the snapshots from the kernel, similar to the trace pipe of trace points, of kernel trace points. As I said, it's possible using the callback that user space triggers a snapshot. So a monitor program can get, for example, a SCSI snapshot. I said that we have ASCII key metadata and binary data, and one idea was that that when you read that snapshot from the kernel, it is done. We package it in a CPIO archive, for example. So you get a CPIO archive that you can then extract at the repository. So almost at the end. That was roughly some ideas that we collected the last months. And last point is action plan. So what could we do in order to improve things in that area? Better Linux FFDC. First of all, we have to somehow define some recommendations. So, for example, which trace points should be enabled in a standard system or in a special system in order to have good FFDC. Probably you won't enable all trace points, I think. So you have to think about what is really important. Then, of course, how much overhead is acceptable. As I said, our colleagues told us 2%, I don't know. Then probably you have to define some error classes, so you have an idea what you automatically want to detect. Then one point is to enable traces for FFDC. One point, for example, we saw it for kernel trace points. For example, don't know, Stephen Oster, is he here? You?
He was here earlier, but now I don't see him.
Yeah, okay. For example, it's not possible to define when you at kernel startup a basic set or a startup set of trace points that you want to use, and it's not possible to define instances for wraparound buffers that where you want to store those trace points. That is all done in user space, so it would be good to have that from right from the beginning when you boot your kernel. That would be one point. And the other point is probably to define an access so that you can store kernel traces and also user space traces, LTTNG for example, in snapshots, because this is important information, history information that you need for FFDC. So there must be one. We must think of good ways to access the trace data. Then, of course, somehow you must think of, because I said, if you have a problem in a specific area, you don't want to extract all the states, but you have to know which state. And because every system is partitioned in many different subsystems or components, it's important to know the relationship between the components. For example, which components are responsible for file system I/O, for file systems, for block I/O, and so on. How are the relationships? Many of these relationship information much of this is in the sysfs, for example, via softlink. Because you find, for example, your block device driver, you find the devices of this block device driver. So many things are represented in sysfs with softlinks, for example. Then as I said, define. This is this state safe thing which I've tried to explain. So we have to define which is the relevant component state, and we have to define somehow this, and that was the picture, the repository and the transport mechanism to get all that data to the right place. So that was it. As I said, 5:30 for everybody who is interested. That would be nice if we see you again there. And now I'm at the end, and thank you for your interest.
I'll start with one question. Are you aware of the mini core dump initiative? You are.
Mini core dump. I'm aware of the there was a, you mean for kernel? I saw that there was a kernel patch upstream where they get a component core dump. That was in the last merge window, I think. Is that what you're talking about?
But also there's other things. I mean, many of the things that you're presenting here are part of, I don't know what name they will give it, but Thomas Flexner made a presentation at the Tracing Summit. You can see it on the wiki, where many of those things are there, like what you've talked about, getting LTTNG information in the dump, and many of those things are there and are working. So it might be very good to have a discussion and see what are the common things. And I think this is an example of what Brendan was talking about earlier. I mean, we don't do very good marketing of Linux and when we do those types of tools, so many people are not even aware that this thing exists and it works this way, so we should definitely talk a bit more.
Yeah, that would be good. That was also a reason to be here. So if some of the things that we are missing are already there and we just don't know it, it would be good to know these things, of course.
So I believe it's Sebastian from Linitronics who did a lot of the work, and Thomas Flexner, who's also in Germany.
Thomas Flexner? Yeah, I know him.
Other questions, comments?
So I basically have the same question. There is ftrace, and as far as I understand, FFDC provides snapshots and
should provide.
Okay.
It's just concepts. We have nothing. We have no code. We are just that's just concepts.
Okay. Sorry.
Sorry, I have to make that clear. It's just concepts.
Okay. So regarding the tracing, you already have ftrace. So how should FFDC be different from that?
Yeah, ftrace and also kernel trace points, or this is for tracing. So you have, this is to collect continuously information. And FFDC and all that snapshot stuff is you detect the error and then you have to collect, and this is history information that you collect all the time. And our idea for FFDC is you detect the error and you have to do two things. You have to collect ftrace, for example, the tracing or trace point buffers that you have collected, because this is your history, and then you collect state. It's like a mini dump, mini dump where you collect the current state, and you package this all together into a snapshot. And then you have hopefully enough information. You have the state information, you have the history information, and both together gives you the possibility to reconstruct some history. That's the idea. So tracing is not the same as FFDC. It's a part of FFDC, I think.
So yes, I was perhaps misled by the function definitions there. But what you are telling me is basically there is a kernel state dumping and user space dumping plus ftrace.
Plus so tracing.
What we already do is, for example, we start some task with tracing included, and for example, cyclic test. If you use cyclic test, then you can get your tracing stopped at the moment when a latency passes a defined threshold. So basically, if you are talking about core dump of kernel, core dump of application, and tracing combined, it sounds that the infrastructure is already there, and you should only provide the glue that combines.
Yeah, maybe it's just the glue. Yeah, many things are probably there. And you have to, but for example, there is no general infrastructure for getting these snapshots. When you told me right now, you wait for an event, look at your traces, you saw that latencies are bad, and then you want to get the trace stored somehow, right?
Well, they are provided in SysFS, but you have to
Yeah, you have to extract it manually, and it would be good to have some data store where you can, or mechanism where you just say, now I want to create a snapshot, I want to store it in this repository, and so that it's there for you. That was the idea. Okay.
Hi. I have a comment. For example, for that mini-dump thing, the gaming platform Steam already uses that mini-dump thing, and then there's Google Breakpad with a lot of tools to convert, for example, mini-dump files into core files, and then the core files can be loaded with GDB, for example.
So that was the mini-dump thing?
That mini-dump thing, perhaps have a look at the gaming platform Steam. They also don't send it with any permission, so
okay.
I don't really like that. So I'm developing a library to block all network access for that thing, and to hack it a little bit.
Okay.
Okay.
Yeah, so the initial version of the mini core dump, they needed to have GDB there to resolve symbols and other things, but the current version, I don't think it's necessary anymore to use GDB. So we have those two versions now for the mini core dump.
So and it's an open source project. You can download it from somewhere.
As I was saying earlier, we're not very good at marketing. So I think it's on GitHub somewhere. So that's one of the reasons why we're doing the Tracing Summit and why we want to have the diagnostic and monitoring work group at the Linux Foundation. And this is an example where we will most likely host this at the work group. So it will have a bit more visibility, people will know about it, it will be easier to download, it will be easier to improve and have discussions on it. So you probably want to be involved in those discussions.
Okay, that's good. Okay, maybe one last question? No? Thank you, Michael.